Welcome to the lecture series on tricks of the trade in deep learning with neural networks. This video covers weight initialization. Here is the sketch of a network, and neurons in the network have a transfer function, either the sigmoidal one or the rectified linear unit. Now suppose I apply here in the input layer a first pattern, and I look at the activation A of this first neuron. So pattern number 1 may give an activation of plus epsilon, pattern number 2 an activation of alpha, pattern number 3 an activation of minus alpha or minus 2 alpha, and so forth. But we can also look at pattern number 1 and take different neurons. So pattern number 1 for neuron 1 for the red neuron might give an activation of the value of epsilon, whereas pattern number 2 for the whereas the same pattern number 1 for the blue neuron might give an activation of minus 4 alpha. So for a network to really exploit its nonlinearities, it's important that different patterns give different activation of the same neuron, for example the red neuron, but also that the same input pattern gives different activation of different neurons, like the red and blue neurons. So let us now focus on a single neuron, say the red neuron, and look at its activation. Well, we suppose that the database has been pre-processed such that for each input unit, the mean is exactly 0 and the variance is exactly 1. So when you get your original input vectors, you pre-process, you average across all patterns, you subtract the mean, you calculate the variance, and you reshift the variance to 1. So now we know the inputs are normalized. And now we have to choose our initialization of the weights in this first layer. We have the freedom to choose whatever we want, and we choose to take weights randomly with a mean 0. Okay, so now the mean is 0. But how should we choose the variance? Say we take a Gaussian distribution of weights, the mean is 0, good. What's the variance? And now the claim is that it's important to consider the number n of inputs. I have n inputs plus 1 threshold inputs. Let's call n the dimensionality of the input, and the scaling of the variance should depend on this number n, and the square root will appear. And now I will give you the mathematical arguments why this square root of n is important. And here come a couple of steps of the theoretical argument. Again, the assumption is that the mean of each of the input units is 0 and the variance of this input j is 1, and this is true for all j's, for all inputs. And then we said already that we put the mean of our weights at initialization to 0. Our task is to choose the variance of these weights, and to do that we will look at the distribution of these activations in layer 1. Let's look at the red neuron. The red neuron is neuron I in layer 1, and it gets the input, which is the sum over all these different inputs, wij, xj, and then we subtract the threshold, and this is what I call the activation variable of this neuron j in the first layer. So once we have this activation variable, we can now ask, what's the mean of this activation variable? Again, the activation variable is this variable, it's the input to this neuron, and the neuron will transform it to an output either with a sigmoidal or with a rectified linear function. I'm interested in the mean of this, the mean across the patterns, or the expectation across the different patterns. I sum over all these different inputs, and now we can exploit that the mean of the inputs is 0 and the mean of our weights is 0. Now when I put the mean of the weights to 0 and when I randomly initialize the weights, I did not look at the patterns. So those two are not correlated. It's independent. Therefore, taking the mean of this sum means I take the mean separately. I take the mean of the weights and I can take the mean of the inputs x. So let's continue the calculation. So we have here the mean of the weights, the mean of the inputs. They are independent. The averaging sign is taken independently. Each of the two terms is 0, so this is 0. So that's good to know. That means this red neuron here, this red neuron gets an input which has mean 0. So it's centered around this region here. And the question we ask is, what's actually the variance? Does it just stay in this small regime, or does the variance extend over a much larger regime? So we need to calculate this variance. This is the variance of this input. We know that the mean is 0. And now it's the same argument as before. When I initialized my weights randomly, I didn't know anything about the input distribution. Therefore, the averaging signs can go inside and they are independent. So this average is independent of that average, and therefore I can perform the averages. And what I get is, well, this has average 1. Each of these terms has an average that I want to calculate. And I have n of these terms, and therefore I have this factor n which appears here. And so now I can make the following argument. Suppose I want to exploit a bit of the nonlinearity of this sigmoidal function. So I want to get outside the linear regime. So basically I want to be in a regime like this. And that would roughly correspond to an activation variable that changes from -2 to +2. So if I want this to be in the range of 2 or square root of 2, then I know how to choose wij squared. I know I can calculate, I can predict a variance of the weights such that the variance of the activation is in the desired regime. So let us summarize this little calculation for the input layer. We assume that the database is normalized to mean 0 and variance 1 for each input unit j. We work with weights that are initialized with mean 0 and with a standard deviation 1 over square root of n, or 2 over square root of n, or 3 over square root of n, not 100 over square root of n. 1 or 2 or 3 are good numbers. And this gives a reasonable distribution of the activations in layer 1 and therefore also of the outputs xj in layer 1. And now we know that these guys here are reasonably normalized. And now we can repeat the argument and say, well, these neurons here, the outputs of these neurons are the inputs of neurons in the next layer. And so we should now initialize the weights here so that we also get a reasonable activation in the layer further up. So if we manage to normalize the variance of the outputs to order 1, then we are fine and we can initialize the weights here with the same arguments that we used for initializing the weights down here in the first layer. Let's look at the backprop algorithm. In the forward pass, We take an input pattern, which takes us to the first layer, from there to the second layer, from there to the third layer, and finally to the output layer. And each time we need to evaluate these nonlinear transforms of the inputs. If we want that all of these neurons are exploited in the nonlinear regime, then we have to make sure that the weights in each layer are suitably initialized with mean 0 and a variance appropriately chosen, and the variance should scale with a number of inputs to a given layer. So why is the initialization of weights so important in backprop? Well, as we have seen, different patterns will cause different activations of a given neuron. So for the red neuron, pattern 1 will cause an activation of +2 epsilon, pattern number 2 a activation of -5, pattern number 3 a activation of +alpha, you name it. It's important that these activations do not all stay in the linear regime. If all of these activations stay in the range of plus and minus epsilon, then the neuron, the red neuron, is in the linear regime. But then the other neurons will also be in the linear regime. And this is then true in all layers. Layer 1 acts as a linear transformer, layer 2 as a linear transformer, layer 3 as a linear transformer. So the whole network is just a linear transform. But then it's not a good network. It cannot perform the tasks we want it to do. So initialization requires that we are not, for all patterns and all neurons in the linear regime, that we really get out of this linear part. So the arguments that we used for the initialization should be used at each and every layer. We need to get out of the linear regime. So for piecewise linear activation functions, if the mean is 0, then different patterns are automatically, even if one pattern is plus epsilon, one pattern is minus epsilon, different patterns touch different parts of the gain functions. So even though it's piecewise linear, across patterns, it's a different linear function that's used. And that's why the network as a whole is immediately from the beginning a nonlinear network. If I use sigmoidal functions and all the activations are in that regime, then it's always the same linearity that is used by all neurons in a given layer, by all neurons across different layers. Therefore, for sigmoidal functions, I have to make sure that I get out of this linear regime, out of a range which I call alpha, and alpha is probably an activation variable of 2 or 3. So if all patterns in all layers touch the linear regime of the transform G of A, then the whole network is linear. The aim is to initialize the weight such that different patterns touch different regions of G of A. And this is automatically true for ReLU if the mean is set to 0. But that means we have to make sure that the mean is 0 in all layers. And this is automatically true for sigmoidals if the variance across patterns is larger than 2 or larger than 3. And just to make this point, let's look at a standardized sigmoidal unit, also called the logistic function. For A equal 3, I have a value of 0.95. More importantly, in our current discussion is that in the range from -2 to +2, it's more or less linear. Once I get in the regime of 2, you see that the curvature is high, and that means that the slope changes a lot. So a pattern sitting here exploits a different linear function than a pattern that activates at around 0. And if this is piled up in a deep network, we really exploit the nonlinearities. We implement a nonlinear mapping of different input patterns to the output. To summarize, we need to exploit the nonlinearities during the forward pass. I call this the linearity problem. Linearity is a problem if the weights are initialized very close to zero. So we have to make sure that the initialization of the weights is well chosen, such that the mean across patterns is zero, and the standard deviation of this activation variable should be of the order 1. Could be 1 or 2. And then, and this is not yet part of the current lecture, and then we have to make sure that after the backward pass and after the weight updates, that these arguments, these means, these variances don't change too much. So we don't want to go immediately back into the linear regime. But this will come up in one of the next parts of this lecture. Okay, let's finish with a little quiz. You may want to pause the video for a moment to look at the slides before you make your commitment. Before we start here, a little introduction of this number Ni. Ni denotes the number of input connections onto neuron I, and this number is also called the fan-in of neuron I. And now we start with the first claim. A good initialization of the weights onto neuron I is a Gaussian random distribution with mean 0 and variance 1 over Ni. If you agree, raise your hand now. And yes, this is correct. This is what the calculation was all about. Second claim. A good initialization of the weights onto neuron I is a Gaussian random distribution with mean 0 and standard deviation 1 over square root of Ni. If you agree, raise your hand now. And yes, this is also correct. This is in fact the same. The only reason I put it here because this is how it's usually written down in the textbooks. Third claim. The fan-in number Ni and the above rule for random initialization includes the threshold variables. If you agree, raise your hand now. And this is wrong. Remember, in the calculation, I only worked with the weights. I left out the threshold variable. So, what do we do with the threshold variable? Here's a claim. A good initialization of the threshold variable in all layers, in all neurons, is 0 or very close to 0. If you agree, raise your hand now. And this is correct. There's no reason to go away from 0. In fact, if you would move out the threshold to a large value, that means you move out the mean to a large value, and then for the ReLU, different patterns would not touch different parts of the piecewise linear function. So keep it close to 0 or keep it at 0. Final claim. The choice of the standard deviation of the random weights during initialization is less critical for the ReLU than for the sigmoidal units. If you agree, raise your hand now. And yes, this is correct. So, first point for the ReLU. Let's see how we continue.